This is a review of the state space quiz in the Process Dynamics and Control course. And we're going to, if you want to start, get to the course homepage, go to course schedule, and then scroll down to the state space material. Down with state space models, there's a quiz, a simulation assignment, and then also a TC Lab activity. So we're going to go first of all to the state space models. This is the background on state space, and it gives a little bit more information on state space, stability, first order systems in state space, second order systems in state space, general nonlinear systems and how to convert those back into state space form, and then also an exercise that shows how to set up and simulate some of these with a solution video there. After you complete that, I recommend that you come here to the quiz that we're going to be covering today. So the first question is, what is an advantage to put equations into state space form? So there are 3 correct answers, and the very first one is correct. The eigenvalues of the A matrix of this one right here determine the system stability. And there's another question down below to show if the system is stable or not based on an eigenvalue. Nonlinear equations are more easily analyzed. So that one is going to be false because state space models are linear, at least the linear time invariant form like I show here. And then it is a compact way to express systems with multiple inputs and multiple outputs. Now that is correct because U is our input, and that can be a higher dimension. So if that's 1, you have a single input, and then Y is our output. So if you have that as more a vector of length more than 1, then it has multiple outputs. So that one would be correct. And then the third one, the model is in time domain that is more intuitive than other forms such as a Laplace domain. Now I guess that one might be debatable, but you know, I think we're all used to time domain and differential equations in the time domain, so it can be more intuitive. But if you're very familiar with the Laplace domain as well, that one is maybe debatable there. All right, here's number 2. Which of the following equations is equivalent to state space model with A equals -5, B equals 2, C equals 1, and D equals 0? So let's go ahead and just write that out here. I have x dot equals, and then I'll have A, and that's going to be -5, all right, times x, and then I have B, which is 2. All right, so I have 2u, and then I have y equals, and in this case it's going to be 1 times x plus 0 times u. So this equation right here is basically just y equals x. And if I plug that back in here, and then also the derivative, then I come up with answer C. Okay, so that one is going to be the correct answer because I've reduced this down just knowing that the output y equals the state x. All right, let's go down to the next one. Which of the exercises or these problems has multiple states? All right, so we have a first order differential equation, second order differential equations. We have also second order differential equations expressed as with a second derivative of y, and then we have some nonlinear differential equations as well. All right, so which one has multiple states? For the states, let me go ahead and just some of the notation from before. X is in set of real numbers n by n, so that these are the states right here. And in this case, if x or sorry, I guess I should have said A here. Okay, A is going to be real numbers. This X is going to be the number of states. It's real numbers of dimension n. All right, and so what I want to do here is just look at these different systems and see how many x values we have. Okay, so this very first one right here, we only have one x value, and that's because we only have one differential equation. So it's the number of equations or the number of x values. So in this case I have two x values, so I have two states in my system and only one output. In this case I have a second order differential equation, but it's not in state space form. I would need to convert that into state space form that would look like this one right here, because I would have to define two differential equations to get my output. Alright, and then nonlinear differential equations, I could linearize those and get it back into a two-state form. I do have two outputs here though. Okay, but still only two states. So the question is, how many states, which has multiple states, and in this case it's going to be B, C, and D, and all of those have two states. Alright, let's go on to the next one. The A matrix of a state space model has eigenvalues, okay, and it's 0.45 plus or minus 2.1i, there's our imaginary number, and then minus 3.1. What conclusions can be drawn about the system stability and oscillations? So what we look for with stability of these systems when they're in state space form is if any of the real numbers are positive. And in this case we do have at least one root, in this case two roots with a positive real number, so that we know that the first part of this is that it's going to diverge. And then we also want to see if there are going to be oscillations or no oscillations. And so if there are imaginary numbers in any of the roots, in this case there is one that has an imaginary number, then it's going to have oscillations. So it's going to diverge with oscillations. Let's go ahead and select that one. So the solution is there are imaginary parts, the eigenvalues, and a positive real part to at least one eigenvalue, so the system response diverges and is not stable. And then we can just verify that. Here's some source code here with that you can use if you want to. Plug that into Python, and in this case I've set this up as A, B, C, D matrices. Okay, and then we have our eigenvalues there that we're going to print out using NumPy linear algebra package, and then we're going to convert that to a state space model and then do a step on that state space model. So step the input, and there you can see that you start to see oscillations, and the oscillations grow until about 15. I mean, it's going to continue to grow, and so that's why it oscillates and is unstable. Alright, well that concludes the quiz. I hope you were able to test your knowledge and tried it out yourself before looking at the solutions. The next one is going to be going on to an exercise that involves a reactor in state space form, and where you can linearize and put it into this state space form, and there's a starting script as well that you can use to simulate that. Alright, and again another solution video right there. And then the final thing for this series of exercises is putting the temperature control lab model into state space. So there's the full nonlinear model, and we're going to put it into this state space form, basically calculating all of these A values, B values, C and D matrices in our state space model, and those are going to come from the partial derivatives of each of the variables, each of the states that I have. Okay, and then here's some code to help you get started. That one's a little bit longer, so I do recommend go to the solution if you need some help with this. Okay, and there's also solution here with the linearized system, and you can compare it to the nonlinear response.